Hey guys, this is 12.2, day 4, and what's math, especially limits, if we didn't do some word problems. So here we go. Let's get started. So these are ones where you're going to be given, let's say, a formula or an expression and so on, and you're going to be asked, what is the limit of, the function when one of the variables goes to 0 or infinity. You may recall that in the beginning of after we did trig, when we had talked about limits, we had a couple of formulas there, like the formula for the theory of relativity. And then, I remember everybody kept coming and asking me, but I'm not clear on this. What am I going to do? And I just sort of, kept putting you off. And I said, we're going to get back to it. We're going to get back to it. And look at us now. We've gotten back to it. It actually is going to feel better now that you've had some time to digest that. So without further ado, let's just get in here. Here's an example. It says the width in millimeters of an animal's pupil, yes, we're now measuring an animal's pupil, is given by this formula, where x is the illuminance of light shining in the pupils and is measured in lux, L-U-X. Okay, why do I choose this problem every year? It's because there is a lot of terminology here, and there's a lot of things here that we've never talked about, that you've never heard. But you know what? It does not change the math that we're going to do to solve this problem. So that's why I kind of do this, and I want you to be able to sift through information. All right, so we all know that your pupils will dilate or contract depending on how much light there is in the surrounding, right? So like in the morning, when it's bright, your pupils will contract in order to not let in too much light. But then when it's dark, your pupils will dilate in order to let in a little bit more. So that's what's happening here. The width of the animal's pupil is changing based on how much light is shining in the pupils. Okay, write a limit to describe the width of the animal's pupil when the light, right, this is x, is at its minimum illuminance. Then find the limit and interpret your results. So basically what we're talking about here is the limit of d of x as x, the illuminance, is approaching 0. So this is the limit as x approaches 0, right? As the light x is at its minimum, which means x is approaching 0, because what's the lowest amount of light there is? There is no light. So when we're getting to that minimum. So the limit as x approaches 0 of that mess of a formula right there. So 152x to the negative 0.45 plus 85. 4x to the negative 0.45 plus 10 is equal to, now we're going to have to do some algebra here. This is the limit as x approaches 0 of, okay, what's x to the negative number, right? So I'm going to go up here. If you have x to the negative 2, what's another way to write that? 1 over x to the positive 2. Well, okay, if you have 152 x to the negative 2, how much is that? It's 152 over x to the 2, right? So if I have 152 x to the negative 0.45, that's 152 over x to the positive 0.45 plus 85. And same thing here. Now we have 4 over x to the 0.45 plus 10. Okay, well that is a bit of a mess. Yes, it is. That's a bit of a mess because we're still not at the point where we can simplify this. Okay, so what I'm going to do right now is I want to get rid of that bottom x to the power of 0.45. Okay, so what can I do to do that? Well, I'm going to make a common denominator, right? So I'm going to work on the bottom first. So if this is 4 over something, well, I'm going to multiply the 10 by x to the 0.45 over x to the 0.45. I'm just making a common denominator. And let's do that here. I know there are lots of ways to do this. I've found most students find this easier. So now I have 152 plus 85 times x to the 0.45 all over x to the 0.45. And then 4 plus 10x to the 0.45. And there is a method to this madness here. There is a reason why I'm doing this. And it'll become clear in part B. Over x to the 0.45. I know there are other ways to simplify this one, but just bear with me here. Okay, so now anything cancels here? Well, yeah, this cancels and that cancels. So now I have that this is the limit as x approaches 0 of 152 plus 85 x to the 0.45, 150 over 4 plus 10 x to the 0.45. Okay, that's much, much, much better. All right. Now I can plug in x equals 0, right? So before, at this step, could I have plugged in x equals 0? No, I would have gotten 4 over 0, and that I couldn't have simplified. But now that I have no x's essentially in a denominator, I can do this. So now when x is 0, I have 152 plus 85 times 0 over 4 plus 10 times 0. So that's 152 over 4, which is equal to 38, right? Okay, so that's that. And now it says find the limit and interpret your results. So the interpretation of this, what is the meaning of this? As x approaches 0, x was the light. So when the light is at its minimum, the pupils contract to a minimum width of 38 millimeters. Okay? All right, if we are calculus bound, and if this, like I said, is the first chapter of calculus, then we must be able to explain our results in coherent English using proper mathematical terminology and units. All right, so here it says, now write a limit to describe the width of the animal's pupils when the light is at its maximum illuminance, then find the limit and interpret your results. So this time I want the limit as x approaches infinity of that god-awful function. But now I simplified this function, right? So I could technically use the function at any step because I've simplified it. So you know what I'm going to do? I'm just going to use the most simplified version, which is this 152 plus 85 x to the 0.45 over 4 plus 10 x to the 0.45. Isn't that cool? That's so cool. All right, so now let's take a look for a minute. This is the limit as x approaches infinity. All right. And so now, if it's the limit as x approaches infinity, what do? All I have to do is look at the term with the highest exponent, right? Well, in this case, it's x to the 0.45, right? So I just take this, over this. So the term with the highest degree, Because what's the exponent for the 152? That's x to the 0. So technically x to the 0.45 is still higher. All right, so take a look. The degree on the top is equal to the degree on the bottom. That means the limit is just the ratio of the coefficients. 85 over 10, which is 8.5 millimeters. And so to interpret our results, as the light approaches a maximum illuminance, I'm having trouble with my pen, I'm going to abbreviate illuminance, the pupil's width I'm gonna abbreviate, the pupils dilate to a maximum length of 8.5 millimeters. Okay, obviously the semantics of it can vary. It's what is important, right? As the light approaches a maximum, that's important. Maximum, okay, and then the 8.5 millimeters with the units is important, right? The pupils dilate, length of 8.5, right? Okay, let's move on. Here's another lovely formula from molecular theory. In molecular theory, the root mean squared speed measures the average speed of particles in a gas, defined by this formula. Yes, this comes from PV equals nRT, right? So this is the V, root mean squared, where R is the gas constant, T is absolute temperature, and M is the molar mass of the gas in kilograms per mole. Fine. Again, right? Again, if you're taking, whether you're taking AP tests in math, in calculus, or you're taking SATs, the trend now is to just inundate you with lots and lots of words and information and see if you are able to sift through all that information. What are we looking for? We're looking for the limit as m approaches 0 of V. So the limit as m approaches 0 of V is equal to the limit as m approaches 0 of the square root of 3RT over m. And now, what happens as m approaches 0? What happens if your denominator approaches 0? That means you're dividing by a very, very small number. And when you're dividing by a very, very small number, the entire fraction gets very, very large, right? So remember, so the limit as x approaches 0 of 1 over x is infinity. And this one here, this is the variable. As that approaches 0, the whole thing is infinity. And then what's the square root of infinity? It's still infinity. Okay, interpret your answer as the mass. So m was the mass. As the mass of the particles approaches 0, the velocity becomes infinitely large. Does that make sense? If a particle is so tiny it travels super, super fast, that totally makes sense. Find the limit of V as m approaches infinity. We never saw that one coming. So the limit as m approaches infinity of the square root of 3RT over m. And now imagine you've got some, stuff at the top here, right? You've got some food, and now you have to divide it by an increasingly large number. People just keep showing up at your party, right? This was obviously prior to coronavirus. People just keep showing up at your party, and so now you have the same number of food but a large number of people to divide it with. So how much does each get? Practically zero, right? So this is going to approach zero. What does that mean? As the mass of the particles, oh my, I combined, oh my, as the mass of the particles gets infinitely large, the velocity approaches zero. All right, and with that, you can go ahead and do your homework. Have a good afternoon.